Hello friends, welcome to Cadence tutorial. I am Madan Kumar Jha and today in this video I am going to explain how to calculate the noise margin and propagation delay of an inverter using Cadence calculator, and also I will explain how to equalize the noise margin, that is NMH equals to NML. So for that, first you have to design the schematic of this inverter. So I have designed it in my earlier videos, you can watch this. Uh, so Here I am going to simulate the transient analysis of this inverter and then show you the propagation delay. So for that I have to give a pulse voltage at the input of this inverter. So I have already applied, but now I am going to change its properties. So this is the pulse voltage, which is 1.8 volt, and voltage 2 is 0. Okay, the period is 10 nanosecond and 5 nanosecond is pulse width. So I want to see its propagation delay, so I'm giving a rise time of 1 nanosecond. Okay, and similarly fall time is also 1 nanosecond, and I'm going to increase the pulse width to 10 nanosecond and period to 20 nanosecond. Okay, then I will see, yeah, or I can only observe the rise time and fall time in a good way. Okay, so after this, go to launch, then click on ADL, then go to analysis, right click, and in transient analysis set the transient time to 200 nanosecond, then moderate and click on OK. Then in output section I am going to select Y and A. Okay, after this run this simulation. So I have not check and save here, so I am going to check and save. It gives this error. Now run this simulation. Okay, okay, so here there are multiple library selected, so I'm going to change that in my model libraries. I only need GPTK 180, so I'm going to uncheck all, then click on OK and run this. Now I got this waveform of output corresponding to this input. Okay, here the rise time is and fall time is very less, so there will be less propagation delay. Now I'm going to change the style to solid. Okay, so that I can observe it too. Okay, so now you can see this is the input waveform and this is the output waveform of that inverter. Since I want to see its propagation delay, so what is propagation delay? Propagation delay is basically TPHL plus TPLH by 2. You can see here, when the input signal is rising and output signal is falling, then the difference of midpoint of output signal to the input signal, midpoint of input signal, is basically TPHL, which is propagation high to low. Similarly, when the input signal is rising, sorry, falling, and output signal is rising, then the difference of the 50% of the input signal to the output signal is known as TPLH. Okay, and for calculating the propagation delay, I have to add this both and then divide by 2. Okay, so go to this. Then there are two methods for calculating this propagation delay. Either you can use a vertical line or horizontal line. So press B for vertical line and H for horizontal line. So I'm going to press H, and since the VDD voltage is 1.8 volt, so 50% of VDD voltage is 0.9 volt. So set here 0.9. Okay. So if you set here 0.9 or 900 millivolt, then it will go at 900 millivolt. Enter. So this is 900 millivolt. Then at 900 millivolt, I have to set this horizontal line. For more correct result, I am going to create this. Okay. Now move this horizontal line which will coincide here. Okay. Now 11.5 is the 50% of this input signal. Similarly for output signal, again I am going to press B and H for horizontal line, and now change the this voltage level to 900 millivolt. So 900 milli, so this is 900 millivolt. Then you can coincide this with the intersection point of this 900 millivolt with that graph, and then you will find the propagation delay by subtracting these two. That is 11.5, it is 11.5, and it is 11.464. So 11.5 minus 11.464 is basically our propagation TPHL. Okay, so one way is this, you can find using vertical and horizontal line. Okay, and the second way is to calculate this using calculator. Okay, so how can I find it using calculator? So here go to tools, then click on calculator, then in function remove this. Okay, then in function panel, first you have to maximize it. In function panel, search for delay. Okay, then click on delay, then select the signal 1 and signal 2. So here click on signal 1, then go to that plot and select the input signal. Okay, now the input signal is basically rising. So signal 1. Okay, again go to that plot and select the input signal. It should come here. I don't know why it is not coming. Now click on output signal. Again search, I'm going to search for delay, then here click on signal 1. Okay, so first, before this you have to click on wave, and then click on signal 1, and then select this input signal. Okay, now it will go there, I think. Yeah, then again click on signal 2 and go to this waveform again and click on signal 2. So signal 1 is rising, so set the threshold voltage to 0.9. Okay, here also 0.9, and A type is rising for signal 1, and for signal 2 it is falling. Okay, then click on apply, then on OK, and click here. So you can observe it is minus 35.73 into 10 raised to minus 12, that is picosecond. So 35.7 picosecond is the uh, delay, that is TPHL. Why it is negative? It is negative because I have subtracted the 50% of input minus 50% of output. So this minus this, due to this it gives us negative value. Using calculator manually I can also calculate it, which is 11.5 minus 11.5 minus 11.464, which is 0.036, which is 36 picosecond. So manually I got 36 picosecond, and here it is 35.73, which is approximately 36 picosecond. So you can see, so this is TPHL. Now I am going to write here my TPHL is equals to 37 picosecond. Okay, sorry, 36 picosecond. Now again I'm going to calculate TPLH. So for that what I have to do, I have to only change the direction of that signal, because for TPLH what I have to do, I have to calculate this minus this, so this minus this. So it is in this case the input signal will be falling and output signal should be rising. So just go there. Okay, then click on delay, then remove this and this also, and here click on wave, then go to output signal first. Okay, so again click on wave, then click on signal 1. Signal 1 should be output signal. I'm going to select this. So close calculator once. Actually it have calculated the previous value which is saved here. Now click on delay, click on wave, then click on delay, search for delay. So here in all, search for delay, and in delay section you have to choose signal 1 and signal 2. So this is signal 1. Okay, then click on signal 2 and fade the signal 2 into that calculator, and then set the threshold voltage to 0.9 volt. And in this case input signal is basically falling and output signal is rising. So click on this and then click here, then click on apply, and then on OK, and then click here. So you'll get it is 138 picosecond. Okay, so TP LH is equals to 1 TPLH is basically 138 picosecond. Now you can calculate the propagation delay from here, which is equals to TPD equal to 36 picosecond plus 138 picosecond divided by 2. Okay, so this is the way to find the propagation delay in Cadence Virtuoso using calculator. Okay, now close this. So it will be approximately, I think, 138 plus 36, which will be 174 divided by 2, which will be equal to 87 picosecond. Okay, so it is 87 picosecond. Now my aim is to calculate the noise margin and phase and noise margin of the inverter. So for calculating noise margin, I have to first uh, do its DC analysis. So here close this, then go to waveform and then remove this V pulse and press I, or copy this using C and use it here. Now I am going to make the width of this PMOS as variable, which is 2 micrometer. So I'm going to change it's with that W. Okay, and this Q here. Then I'm going to make it DC voltage. Okay, now go to launch and then in ADL remove this transient analysis. Okay, then edit and go to DC analysis, then select component parameter and then select component. So I'm going to select the input voltage because I want to plot the VTC curve. So after that I have to define the voltage level to 0 to 1.8 volt, then click on OK. Now here in design variable, copy from cell view. So here I am going to give the width is 2 micrometer and the control voltage is 1.8 volt, and then run the simulation. So you will find this is the VTC curve, and since I want to see its noise margin. Okay, so for finding noise margin, first I'm going to bold this. Okay, so what is the noise margin? So noise margin is basically uh okay, so noise margin is basically NMH and NML. So NMH is basically VOH minus BIH and NML is basically BIL minus BOL. So what is VOH and what is BIH? So in the BTC curve, where there is slope is -1 at both here and here. Okay, so when the slope is -1, the y-axis corresponding to that slope gives you BOH here, and the x-axis corresponding to that slope -1 gives you BIL. Okay, similarly the y-axis corresponding to this slope -1 gives you BOL, and the x-axis corresponding to this slope will give you BIH. Okay, so this is the BTC curve. Now I want to plot the derivative of this curve, because when I will plot the derivative of this curve, then I will see where it is -1. Okay, so for this, click here, then send this graph to calculator. So click on calculator, then select here derive or search for derive function. So this is derive. Click here, then click on this. It will plot the derivative of that VTC curve on the graph section. Okay, so you can see here, delete this. Okay, now you can see here, this is the plot of derivative. So where the derivative of this BTC curve is -1, I have to find the x-axis and y-axis corresponding to that. So for getting -1, I am going to press K, horizontal or vertical line. So press B. Okay, now set here -1, or press horizontal line H. Okay, then set here -1. Okay, so when you will set -1, it will be here. Then zoom this. Okay, then the graph intersect this horizontal line at 612 millivolt. You can see here. So 611.7 or 612 millivolt. Okay, so I'm going to slide this to 600, or intersection point of this. Okay, so this is the intersection point of this. Okay, so the y-axis corresponding to this intersection point will give you VOH. So VOH is basically 1.711 volt. So I'm going to write here VOH and VIH. Okay, or I'm going to copy this. Okay, again Control C or Control C, then paste here and delete this all. Now VOH is basically 1.711 volt, 1.711 volt minus VIH. So the y-axis corresponding to this gives you VIH, and the x-axis corresponding VOH, and the x-axis corresponding to this will give you BIL. Okay, so BIL is basically 612 millivolt. So BIL is 612 millivolt. Okay, or you can, am I right or not, you can verify it. So go to Google, then click here VTC curve of inverter with noise margin, then click on image, So you can see here. So this is BIL and this is BOH. So the slope corresponding to this slope minus 1, the x-axis corresponding to that give you BIL. Okay, so I am right, I am correct. Okay, so this is BIL. Then similarly the slope minus 1 corresponding to this curve also gives you the vertical line corresponding to this gives you BIH and BOL. So again press B and slide it to the intersection point which is here. Okay, and then this 79 millivolt is your VOH and 860 millivolt is BIH. So BIH is 860. What is BIH? BIH is 860 millivolt. Okay, so 860 millivolt. I am going to convert this also in millivolt, so it will be 1711 millivolt minus VI VOL. So VOL is basically 79 millivolt. Okay, minus 79 millivolt. Okay, so you will get NML equals to 612 minus 79, which will be 533 millivolt. Okay, and NMH is equals to 1711 minus 860 millivolt, which is equals to 851 millivolt. So here the noise margin high and noise margin low have some differences. It is 851 and it is 533 millivolt. So uh, there are some disadvantages of this because the noise margin high is 851 millivolt. So this signal is passes noise weaker to 1 and stronger to 0. So what is, so we need to equalize this noise margin, that is NMH equals to NML. For that what should I do? So first I am going to see the benefit of this equalizing noise margin. So after equalizing noise margin, both margins are equal. The circuit can tolerate the same amount of noise for both logic 0 and logic 1. So the circuit in which you use that inverter, it can tolerate both logic 1 and logic 0 by same amount of noise. Okay, this balance the robustness. Okay, one other benefit is the inverter rising and falling transistor points are balanced. Okay, giving consistent propagation delay. So it will give you consistent propagation delay, that is the propagation dphl and tplh will be equal. Okay, and since most CMOS logic gates are built from inverter having a symmetric VTC, makes sure that when you connect multiple stage logic levels remain stable. So there are some advantage of this equalizing noise margin. So for equalizing noise margin, what should I do? I have to change the width of this PMOS or either PMOS or NMOS. So I am going to close this and I am again going to this, and this time I will do its parametric analysis. So click on tools, then select parametric analysis and add variable. So click WP or W. I think my design variable is W. Okay, so this W is the width of this PMOS, and I want to see this width from 2 micrometer to 10 micrometer. I'm going to vary this to 2 micrometer to 10 micrometer. Then total step mode is linear. Okay, and then total step is 10. Okay, and after that go to ADEL, then here go to tools, click on calculator, then from calculator click on VS, then select that output signal. Okay, so here is my output, so I'm going to select this, then go to calculator again, search for cross function. This cross function will give you set the threshold to a particular value. So actually I want to set the threshold of that VTC curve to 0.9, because if I will set the BM to 0.9, which is half of the VDD, that is 1.8 by 2 is 0.9, then it will give you uh, equalized noise margin. Okay, so noise margin will equal only when BM equals to VDD by 2. So apply, then click on OK, then go and run that simulation parametric analysis. You will get the result. So after completing this parametric analysis, you will find the value of width of that PMOS W with corresponding to 0.9 volt, and after setting that width, uh, you will get the equalized noise margin. So after this analysis, I will again recalculate the NMH and NML, and then I will show you that NMH is equal to NML, and there this inverter have equal noise margin NMH and NML. Okay, so there are multiple curves here. Parametric analysis. Okay, and fade this. Sorry, actually I have not fade this cross value to ADEL, so why it have not come here. If I will run this simulation, then what will happen? Okay, so after fading this cross value to here using calculator, so for fading you have to click on this. Okay, and when it will reach here, then run this parametrics analysis. Okay, so I'm going to set this linear step to 8 only, then click on OK. So it will give you two plot. Yeah, you will get two plot here, one for this and another for this, but only I want this plot, no, this plot, not this, so I'm going to delete this plot. Okay, then actually I want to see the value of this width corresponding to 900, so which is 7.4246, or press H, set here 900 millivolt, 900, enter. So you will get 7.4427, 7.4427, set here 7.4427 micro, 7.4427 micrometer width. Okay, and then remove this now and run the simulation. Now this time you will get the VM, which is VDD by 2, which is equals to 900 millivolt. Okay, so it is 900 millivolt when it intersects this. Okay, so now VM by 2 and VDD by 2 overlap each other, so it will give the minimum, the equalized noise margin NMH and NML. If you want to verify, then again what you have to do, click on this plot, then again descend to calculator, then click here derive, and append this, or click here on graph, then it will reach there. Then split this both, remove this one, then press H here and set here -1, enter. The value corresponding to this -1 will give you BOH and VOL. So okay, I'm going to bold this both. Style to solid. Okay, now press B, and the intersection point of this will give you BOH. So press V, then C, intersection of this, and the BOH is 1.6695 volt. So 1669 millivolt, 1669 millivolt, 1669 millivolt. So again I'm going to copy, 1669 is our BOH 16. Okay, and corresponding BIL is 779.7 and 780 millivolt. Okay, so 780 millivolt is my BIH. Then again go there. Okay, already there is a horizontal line, vertical line, so the intersection point of this will give you, this is the intersection point, so it gives 76 millivolt is my BOL, and 1.03 is my BIH. 1.033 1036 millivolt. Okay, and VOL is basically 76.14, so 76 millivolt. Okay, sorry, 76 millivolt, and 1036 millivolt. Remove this and this. Again, I'm going to see what is the value of this. 1.65 and 795. 1.65, 795, sorry, 1.65 and 779, that is 780. Yeah, good. Now subtract this both. So 1669 minus 1036, which is 633, and it is 780 minus 76, which is equals to 704. So there is minor mistakes in calculations, because here you can see the intersection point of both is not clearly visible, so it will give some minor issue, because it is in millivolt. Okay, so no need to worry. It is 704 millivolt, 633 millivolt, which is approximately, I can say it is equal, but it is not digestible. So if you want more accurate, then you should find this intersection point accurately, then subtract this both. 166 minus BIH, which will be equals to 9. Actually this is minus 1. Oh, sorry. Yeah, this is minus 1. So at minus 1 it is 78 millivolt. 78 millivolt is this, and 78 millivolt, and the another one is 1.03. 1.03. So 1036, it is 1034. 1034. Okay, yeah, it's correct. And similarly here also you can find 1 at minus 1. Yeah, so here it is 1669 and 1669 and 780. 1669 and 780. Yeah, so although it is quite large in difference, 3635, and it is 80 minus 76, which will be same, 704 millivolt. So actually this is the process for finding that. So you can find, or you can learn the how to use the calculator tools I've explained. There may be some issue by which this not give accurate result, so don't bother. Thank you.